Okay, we had a very great introduction session about the long roadmap, and the next talk will be presented by Shubhayan Sarkar, and he will tell us about one of the very important pieces, and this is a certification of the optimal randomness using the quantum steering. Shubhayan, the stage is yours.
Thanks, Oxana. So I hope my screen is visible now.
Yes.
Yeah. Yeah. So thanks a lot, Oxana. So hi, I'm Shubhayan Sarkar from Center for Theoretical Physics at the Polish Academy of Sciences. So I would like to thank the Committee of Quantum Science Days to give me an opportunity to present my work for the second time. So without me wasting much time, let me begin. So I will be presenting today on the topic certification of optimal randomness using quantum steering. So let me begin by describing what is meant by quantum steering. So the scenario is very similar to Bell's scenario. So there is Alice, there is Bob, and there is a preparation device. So Alice and Bob are spatially separated, and this preparation device prepares a system whose one part goes to Alice, another part goes to Bob. Now Bob chooses some classical inputs, and based on this classical input, some measurements are performed on the system which is received by him. And this measurement gives two outcomes, which are denoted here by 0 and 1. Now, conditioned on Bob's measurement choices and the outcomes, different states are being prepared on Alice's side. And these states in this quantum steering picture are known as the assemblage, which are denoted here by this sigma YB. Now, the basic difference from Bell scenario to quantum steering is that Alice is trusted, which means that Alice can perform a full tomography on the received system. So in fact, she performs a tomography on these sigma YBs, and she can fully construct this assemblage. But we would like to see this in a picture which is very similar to Bell scenario. So we look at this joint probability picture. So what it means is that, let's say that Alice performs some measurement AX and Bob performs some measurement BY, and both of them get an outcome A and outcome B. Then if you are restricted in quantum theory, then you can calculate this probability based on this assemblage and some positive semi-definite operators which denote the measurement operators of Alice. Now you can also express it in terms of the state which is shared between Alice and Bob in terms of this rho AB and Bob's measurements BY. Now it turns out that there exists some set of these joint probability distributions, or equivalently, these are also known as quantum correlations, which cannot be reproduced by any local hidden state model. So this local hidden state model is a notion of classicality, which basically says that any phenomenon which or any statistics which Alice observes in her lab is independent of Bob. So and because here Alice is trusted, so it's like some hidden quantum state is the reason for all the statistics that she sees in her lab. So what is meant by device independent certification? So the general idea is that, let's say that I have a box, and the manufacturer promises that this box generates entangled photons. So now the basic question is, how do I verify it? So I can always break the device and check the source, but then it's like I have already destroyed the device, and then I have to order it again and then again do the same, and then it goes on. But what I can do is I can do a quantum state tomography. But then again, as if the dimension of this system grows, so does the number of, I have to perform more number of measurements, and it grows by the square of the dimension. And also I have to know what is the dimension of the system and which are some of the inherent assumptions here. But the best idea is that I take the two arms of these entangled photons, take them to far away regions. I put some local detectors there and do some measurements locally. And then once the experiment is done, I look at the joint probability distributions, and then if these distributions violate some Bell inequality, then I'm certain that these are actually some entangled photons. Now coming back to one-sided device-independent certification, so the basic difference here is that in these two arms, one of the arms is assumed to be trusted. So which means that you know what measurements are performed on this trusted side. Now, how is it done? So first, a staining inequality is maximally violated by those desired states and measurements which we would like to certify. And then if we are able to prove that if they are unique up to some local unitaries or some presence of some additional degrees of freedom, like some extra state on which these measurements act kind of trivial and do not contribute to any statistics, then we could say that up to these local equivalences, my state is the desired state and my measurements are the desired measurements. So let's take a very simple example to see this. So going back again to the scenario which I showed before, that there's Alice and Bob now performs two measurements, and also Alice performs two measurements. So Alice performs these Pauli sigma Z and Pauli sigma X, and Bob now performs the measurements B1 and B2. Now again, the classical bound of this, or the bound which is achieved by any local hidden state model, is √2. But however, there exists some quantum states and quantum measurements which can go beyond this value, and in fact you can get the value 2. So it was shown recently in 2016 that if you achieve the value 2 for this functional, what it means is that up to a local unity, the only state which is compatible with this statistics is the maximally entangled state, and Bob's measurements are up to some local unities, this Pauli sigma Z and Pauli sigma X. So now building on these ideas, our aim is to find a protocol such that we can certify the optimal amount of randomness which can be achieved by any quantum system of local dimension D. So for this, we first constructed a steering inequality. Okay, so let me first go to the scenario. So here again, there is a preparation device, and then there is Alice and Bob who are spatially separated. Again, Alice performs two measurements, Bob again performs two measurements. And each of these measurements are the outcome. So then we constructed a steering inequality, which is of this form. I won't go much into the details of this, but here are some factors which are related to the coefficients of the state, which will give us the maximum violation. So again, here Alice performs two measurements, which are Z and X. These are again the D-dimensional generalization of Pauli sigma Z and Pauli sigma X. And then the maximum quantum bound of this steering inequality is D. And for instance, it is achieved by this state, this bipartite state, which is like parameterized by these alphas. So these alphas depend on these gammas and deltas of the inequality. And Bob has to perform Z star and X. Now, for a remark, you can see that any bipartite state up to a local unitary can be written in this form. So you have a bipartite state, you take the Schmidt decomposition, and then you can locally rotate it, and then you can always take it to the computational basis, and you can see that any bipartite state can in fact be written in this form. And then we found the classical bound of this inequality, and then we showed that it's strictly lower than the quantum bound. So this inequality is non-trivial. So now we using the maximum violation of the steering inequality, we show that you can actually certify any bipartite entangled state up to these local unitaries. And again, Bob's measurements up to some local unitaries are the ideal ones, which I showed before. So in a way, we are able to certify any bipartite entangled state in using minimal measurements possible to observe non-locality, which is 2. Now, using this result, we move on to showing that any rank 1 extremal POVM can be certified. So the scenario is changed a bit. So here again, Alice performs the square measurements, and Bob performs 3 measurements. So what is meant by an extremal POVM? So let's say that for a particular dimension, I have the set of all the measurements which act on this particular Hilbert space of some dimension. So now the measurements which lie on the boundary of this set are known as the extremal measurements or the extremal POVMs. So you can say that any extremal extremal POVMs are the POVMs which cannot be decomposed or as a convex mixture of other POVMs. And then it was proven some time back that any rank 1 extremal POVM can be written in this form, where you have a projector here of some state belonging to that Hilbert space and some scalar which belongs to which can be between 0 and 1. And also they need to be linearly independent. All the measurement elements need to be linearly independent. And they must satisfy the standard conditions for any POVM, that each of the measurement element is positive semi-definite and they must sum up to identity. Now, because our aim is to certify randomness from this POVM, we consider an adversarial scenario where there is an intruder Eve who has access to quantum resources, that she can perform some quantum measurements, and she has access to the state which is generated by this source. So in this scenario, we want to certify the state which is the measurement which is being performed by Bob. So, but it's necessary here that Eve remains undetected, because let's say that Alice and Bob are doing these measurements and somehow they see that their statistics are different from the ones which should have been in the ideal case. So then they can say that, okay, so someone is definitely looking inside my protocol, and then I will just throw away those statistics and start over again. So it's necessary for Eve to have such a strategy that she is undetectable by Alice and Bob during the run of the experiment. So we just impose such a condition that Alice performs these measurements, which are in fact all the tomographically complete set of measurements for any dimension. And then let's say that these statistics belong to some ideal POVM and some ideal state. And then we impose that, okay, so this statistic should also be in the scenario where there is Eve and you do not trust your measurements and do not trust your state. And then using just this condition, and because we certified our state as shown before up to some local unitaries, and also the 2 other measurements of Bob, we can using this we can certify that this non-ideal POVM, or the POVM which is actually occurring in the experiment, is up to a local unitary this ideal POVM. Now, using this certified POVM and this certified state, we will move on to certifying optimal randomness. So again, recalling the scenario, so there is this Eve who has access to the state which is shared between Alice and Bob, and also has access to the measurements which are being performed by Bob. Now, because our state and this POVM is certified, and now we move on to compute what would happen if Alice would like to guess Bob's outcome from this POVM. So we compute using the certified state and the certified measurement that you in fact get a condition that which is only dependent on the ideal state and the ideal measurement. And then if we impose that these probabilities have to be like 1 by d squared for any particular d, then what you actually see, and then it's defined that the amount of randomness is the log of this amount. So then you actually see that you can actually certify 2 log 2d bits of randomness. And this is in fact the maximum randomness that you can generate from a quantum system of dimension d. So in concluding remarks, what I would like to say is that we first constructed a class of staining inequalities, which is maximally violated by every entangled bipartite state and a pair of mutual n-bars bases, which are again very useful in quantum cryptographic tasks. And then we provided a method of certification of these quantum realizations, which violate our stating inequalities. Using these certification schemes, certification results, we then certify any rank 1 extremal POVM. And using this POVM and the certified state, we are then able to certify the optimal amount of 2 log 2 bits of randomness, which is in fact the maximum which is possible to extract from any quantum system of dimension D. So just for a remark, from a classical system of dimension D, the maximum that you can get is log D bits of randomness. But from a quantum system, this is the first time that we have shown that can securely generate 2 log 2 D bits of randomness. So for the details of this work, you can refer to this paper, which is on arXiv. And so these are the people who were involved in this work. And that's all from my side. Thank you.
Great. Many thanks, Shubhayan, for the presentation, and congratulations with this work completed and already pushed into the publishing. Mm-hmm. And let's see if we've got some questions. For the moment, we have, and also many thanks for the time, because we are very well getting on track after a little bit of a delay in the beginning. And we have a first thanks for the very nice presentation from Daria. And the question is, do you have some visions on generalizing your idea beyond bipartite entangled state?
Yes, so currently we are trying to work out this scenario where we not just find a state inequality for bipartite case, but for multipartite cases. So we have a result for like certifying GHZ class of states, and also some graph states and W state for like 3 qubit. I mean, for the 3 qubit case, we also have some results for the W states. So yeah, we are currently working on that, and hopefully we will try to get something more interesting in near future.
Great, very nice. And we have a couple of more thanks from Luis and Gideon, and they are very impressed and glad to hear about your work.
Thanks.
Yeah, and good. So let me check the Discord. I have so far no messages there.
Yeah, no questions in Discord. Maybe somebody will ask.
Okay, very good. Then we can continue also this discussion and maybe deeper consideration of the questions. The question that was raised on a Discord. I think it's a very great platform to keep exchanging. And I would like to invite you just to, as I did for the previous speaker, to thank the audience and to say goodbye in your native language, I think.
Okay. So like I am from India, so like I speak like 2 major languages there. So it's Hindi and Bengali. So maybe I will tell in both.
Great.
So धन्यवाद आप सबका यहाँ पर मेरे इस सेमिनार को अटेंड करने के लिए. In Bangla I can say something like ধন্যবাদ আপনাদের সবাইকে আমার এই সেমিনারটা অ্যাটেন্ড করার জন্য. হোপফুলি আমরা পরে আপনাদের সাথে কখনো ফেস টু ফেস দেখা করতে পারবো. Thank you. ধন্যবাদ.
This is amazing. Thank you very much, Shubhayan. And looking forward to see you further in other events.
See you.
Wow. Okay, we are going very well in time. A really big thanks to our...
the recording, you can stop.
I stopped recording, I think.
Yeah.
Oh, I didn't.
Yeah, you didn't. It's still recording, so you can stop and we'll start again.